All right, welcome to The Explainer. Today we're going to talk about something kind of cool, the secret language of machines. How do you actually hear one breaking before it, actually breaks?
So, let me start with a question for you. What in the world could a massive failing power transformer and a high-tech faulty jet engine possibly have in common? Well, the answer is pretty wild. They actually talk to us. No, not with words, but they give off all these warnings, vibrations, sounds, changes in heat. The real trick, the secret sauce, is knowing how to listen to what they're saying before it's too late. And that's a perfect lead into our first section, when machines get sick. Because when they do, the stakes are incredibly high. An unexpected breakdown isn't just an inconvenience, it's a catastrophe. We're talking costs that can spiral into the millions, lost production, and honestly, some really serious safety risks.
So to make this real, just think about a common industrial pump. It's not silent when it's in trouble. It'll tell you. Maybe the flow rate drops, or you start hearing these weird rattling or grinding noises. It might start overheating, or you see leaks. All that excessive vibration? That's not normal. Every single one of these is basically the machine screaming for help.
All right, so how on earth do you catch these problems early on? Well, that brings us to this absolutely game-changing strategy called predictive maintenance. It's actually a pretty simple idea when you break it down. Instead of waiting for something to break and then scrambling to fix it, which is, chaos, predictive maintenance is all about getting ahead of the problem. You anticipate the failure, which lets you go in and do proactive repairs. It saves a ton of time, a ton of money, and a whole lot of stress.
And the process that makes all this possible, the real engine behind predictive maintenance, is something called condition monitoring. This is the listening part we were talking about. It's the continuous, round-the-clock tracking of a machine's health to catch those first tiny warning signs.
Honestly, the best way to think about it is like a doctor's checkup, but for machines. Except, instead of a stethoscope and a thermometer, engineers are using some seriously sophisticated tools to check a machine's vital signs. First up, we've got the industry's version of a stethoscope, vibration analysis. See, every machine that spins or rotates has a normal vibration, but when something's off, say a shaft is misaligned or a bearing is starting to go bad, it creates a totally unique vibration pattern, like a fingerprint of the fault. By analyzing these patterns, experts can figure out exactly what's wrong with incredible precision.
Then we have the thermometer, infrared thermography. You might know it as thermal imaging. It's this really cool, non-contact way to literally see the temperature of a piece of equipment.
And this is where it gets really powerful. Just look at this. The difference between a healthy machine and a sick one can be as clear as night and day. On the left, you've got a healthy motor, running cool. But on the right, whoa, that motor has a lubrication problem. And that bright red hot spot is a massive warning sign that it's overheating. You would never see that with the naked eye.
Okay, so we've got all this data now, right? We have the vibration readings, we've got the heat signatures, but what do we do with it? How do we actually translate that raw info into a real diagnosis?
Yeah, we can hear the machine is sick. We can see the symptoms. But what's the actual disease? This is where the detective work begins, using both good old-fashioned human logic and, you guessed it, artificial intelligence.
So one really powerful method that humans use is called fault tree analysis. It's basically a superlogical, top-down way to work backward from a problem to find out what really caused it.
Let's walk through this using our overheating pump. Step 1, you define the big problem, pump overheating. Simple enough. Then step 2, you ask, what could be causing that? Well, maybe it's insufficient lubrication or excessive friction. See the logic gates? For step 3, you keep digging. What causes the friction? Maybe a part is misaligned. You keep breaking it down, layer by layer, until you hit the absolute root cause in step 4. That's the thing you actually need to fix. But for today's super complex systems with just thousands and thousands of data points coming in every second, well, we need a superpower. And that superpower is machine learning. Now, don't try to read every box on this slide, you'll go cross-eyed. The point here is to show you the sheer power of AI. It automates this entire diagnostic process. It takes in all that raw data, like those thermal images, and just crunches through it, finding these incredibly subtle patterns and connections that a human brain, well, we just couldn't possibly spot them. And it spits out a super accurate diagnosis. All right, so we've got these incredible tools, but how do you actually put them to work? How do you implement a real monitoring strategy? How do you hire your 24/7 digital mechanic? It really boils down to two main strategies. On one side, you've got offline monitoring. This is when someone goes around with a handheld device and does periodic checks. The pro, it's cheaper to get started. The cons, it's a ton of work, and you could easily miss a problem that pops up right after a check. On the other side, you have online monitoring. This is where you have sensors on the machine, tracking it 24/7. Yeah, it's a bigger investment up front, but the huge win is that you get immediate alerts. You can catch those totally random failures the very second they start.
And, the experts in this field are pretty clear about it. They say if you're not using online monitoring today, you're basically leaving money on the table and taking on risks you just don't need to. Think about it. Preventing just one catastrophic failure can pay for the whole system, sometimes many times over.
So let's zoom out for a second and look at the big picture here. Why does all of this matter so much? What's the real impact of moving from being reactive to being predictive?
Oh, the payoff is just massive. First and foremost, you get improved safety for everyone working around this equipment. You slash unplanned downtime, which means you maximize your efficiency. You get huge cost savings. And at the end of the day, you just have equipment that is way, way more reliable. So really, it all comes down to this. By learning how to listen to our machines, to understand their secret language of heat and vibration, we get this incredible ability to fix problems before they turn into disasters.
And that leaves us with a pretty incredible thought to chew on. As this technology gets smarter and easier to use, what's really stopping us from building a world where unexpected, catastrophic failures are just a thing of the past?